Come back. No. Oh, that's hilarious. Well, look at your hands.
Good morning, everyone. So I hope you had a great weekend. And now back to the work. So I thought what would be a great start of a working week, and I thought about the game of poker. So let's start with the game of poker. Maybe poker, as we called it last time. And I recall the rules. So the rules are, there are two players, ace and Bob, and the game starts as follows. You have two players, they both ante up $1, and ace receives a card. Then, well, this card can be black or red, depending on what ace sees in front of her. She makes a decision, and this decision may be either a fold or to raise. So if she folds, then Aries will just give her $1 to Bob. So the payoff is minus $1. So Bob, the payoff is plus 1. If Aries decides to raise, now Aries touches the table. She has put $2 on the table, Bob has put $1 on the table, and now he has to make a decision whether he wants to call or to fold. And once again, two options: Bob can fold or Bob can call. So if he folds, he loses his $1, which means Aries receives $1, Bob loses $1. If he calls, well, now the picture is like this. Both players put $2 on the table, and now the outcome is determined by the value of the card. If the original card right here is red, A is the red card. So if the card is red, she receives the whole amount of money over here, so she gets $2 from Bob. If, however, the card is black, it is the black card, well, she loses the $2. So that was the game that we discussed in there last time. And this time I decided to write it as a kind of flowchart. It doesn't really matter how I write this game. So for us it doesn't matter. The important thing is we understand the rules. That's the first thing. The second thing is we will be able to write down the game in the normal form as a matrix of payoffs to the players. And last time we also went to this step, so maybe any questions and clarifications about the game. Anything not clear about the rules? Okay, so now the payoff table. So what happens is we want to describe all possible strategies of the two players. For Bob, he has to make exactly one decision, whether he folds or calls. All the rest doesn't depend on him. So for Bob, we have two decisions. Two possible decisions, possible strategies: fold or call. For Ace, well, she has to make a more complicated decision. So we want a strategy which will describe, well, the whole process of her making the decision. In other words, if she were to describe this strategy to somebody else, this somebody else would be able to play instead of her. Make exactly the same decision as she would have done, would have made. So for Ace, well, her decisions actually depend on the value of the card right in front of her, And then she has to make the following decisions. If the card is red, she might fold or raise, then she doesn't have to make any other decision. If the card is black, she has to fold or raise. So her strategies are completely described by her behavior upon receiving either red card or a black card. And last time and the corresponding decisions would be once you receive a red card, fold, once you receive a red card, fold. Or once you receive a red card, fold, once you receive a black card, raise. Or once you receive the red card, raise, you receive the black card, fold, or raise and fold. So these are the pure strategies for X. Once she communicates that she will be playing according to this, let's say, this strategy, she might as well go out of the room and give her seat to somebody else. He will play exactly in the same way. He will receive either red or black, and he will exactly know what to do. And last time we decided what were actual pairs. So, assuming that the frequency of red card or black card is the same, 50% of the time, we decided that the expected pair of the players was as follows: -1, -1, 0, -3 halves, 0, 1 half, 1, 0. And just to show how we arrived at these numbers last time, let's say what happens for this number, how we compute this number. So this number is about Alice pursuing the honest strategy. If you see red, raise. If you see black, fold. And then we decide what will be the pair in the case when both folds. So half the time Alice is going to receive a red card. In this case, first of all, it's half the times. And then what will happen is let me make this flowchart. She receives a red card, she raises, then both calls, so they are right here, and the card is red, so she gets $2. So half the times she gets $2. Then another half the times she will get a black card, and then once she gets a black card, according to the strategy, she folds, so she goes right here, and she gets -$1. And that's the one half that's written over here. And similarly, you can analyze each one of these numbers. That's exactly what we did last time. And we've seen that, well, if she is forced to pursue a pure strategy, well, she will be losing. I mean, if she has to decide on a pure strategy in advance and announce her pure strategy, which means holding one of those, she is not going to win. I mean, in each one of the cases, there is a reply from both which will lead her to get either 0 or a negative amount. Well, then she decides not to pursue a pure strategy. She decides, well, to mix some strategies in such a way that, well, even if she announces her probabilities, well, she will still be guaranteed to get, on average, some positive amount. And it seems quite plausible that she will be able to do this. Let's say these two strategies seem pretty good. I mean, if Bob is not sure which one of the two strategies is pursuing out of these two, well, she will not be able to make one decision which will always lead to her getting B0. So it seems like mixing these two strategies is a good idea. Okay, why not pursuing these strategies, maybe kind of adding some variation, some unpredictability by using these strategies to improve her outcome. So obviously these two strategies are kind of pure wins for Aries. If she pursues it, one of those she's guaranteed not to lose. In these strategies, well, here she sometimes at least doesn't lose, sometimes she does lose. So what kind of way of eliminating strategies do we have that will tell us that these strategies are actually no good, strictly worse than some other strategies? We have a notion of a dominated strategy. So if there is some strategy that if you pursue it leads to some outcomes, but regardless of what the other player responds, the outcomes are strictly worse than pursuing some other strategies, then we know you should not follow this strategy. Example, suppose that Aries for some reason decides to pursue this strategy, at least, I don't know, 5% of the times. Maybe she has an idea that behaving in a really non-rational way will act on her unpredictability and somehow will improve her game. Well, maybe, but now we expect a strategy and tell her, you know what, 5% of the times you play this strategy. Every time you play this strategy, you would have played instead this strategy. Every time you would have made such a substitution, you would at least not lose. I mean, here you will get the same outcome on the times when both folded. On the other times when both fold, you'll get $2 more. So this strategy is strictly worse than this one. In fact, it is even strictly worse than this one. Because, once again, if you compare this outcome to this outcome, Aries will get $1 more by pursuing this strategy instead of this one. And here she will get $3.5 more. So this strategy is dominated both by this one and that one. So it's not a good idea for Aries to pursue this strategy ever. Not even 5% of the time, not 1% of the time. Every time she thinks about this strategy, she's better off switching to one of those. So let's write this down. And by the way, this strategy is also obviously not really good. I mean, it is dominated once again both by this strategy and this strategy. So the strategy to fold every time and the strategy to fold on red and raising black are both dominated by, let's say, this strategy. This strategy is better than both of them. R, D, R. In fact, the other strategy is also both better than both of them. So, but it's enough to just show that something is better than each one of those. I mean, it could be that, say, this one is worse than this one, and this one is worse than this one. It still is a good reason to eliminate both of them. So now we can simplify this game. Now Aries doesn't have to even think about these two strategies. She knows that they are no good. So now we have a much simpler game. Aries has to make just a choice between two options. Either to pursue this strategy or this one. Alright. Now, as we kind of discussed many times, your security level with your strategies here is 0. The worst outcome in each of the two cases is 0 for her, and well, if she pursues just one pure strategy, that's what she's going to get. I mean, eventually we will realize that she's pursuing one pure strategy, and she will respond in a smart way. Or, in other words, if she announces her decision, both will know what to do. However, she has a way to mix the two strategies. And last time we decided that a good idea would be to understand what is the security level when she does mix the two strategies with some a priori unknown probabilities. So we might try to explore several couple of examples. Let's say be honest half the times, and this strategy is probably will be called in poker bluffing, because she will have at some point a losing card black, but she will still be raising, as if she has a winning card. So this is what's called bluffing. And well, we might want to try to analyze several possible mixed strategies, like bluff 50% of time or bluff 10% of time. But it is better, as we saw last time, to actually think about unknown probabilities. So pursue this strategy x 1% of times, pursue this strategy x 2% of times, x1, x2, and then what kind of pair we will get. On this strategy, so she pursues a mixed strategy of x 1% of time being honest, x 2% of time bluff. What kind of outcome would she expect? False. Well, 0. She will get 0 x 1% of times, and she will get 1 x 2% of times. That's her expected payoff if both folds. Similarly, if both poles, her expected payoff would be 1/2 x 1% of time plus 0 times x2. So 0 x 2% of times. And now we want, so that's expected payoff. Now we want both of these numbers to be as large as possible. So we've seen a trick last time. We would say that these two numbers are both larger than some quantity, which is basically called the security level, the mixed strategy security level for AS. And then we want to make this quantity as large as possible. Subject, of course, to some additional constraint about x1 and x2 being probabilities, which means they are both non-negative, and their sum is equal to 1. And then we know that if we want to find the optimal possible probabilities, best assignment of probabilities to these two strategies, we just have to solve this linear programming problem. Make the expected payoff in both cases larger than some number, and try to push this number as high as we can. And maybe it's worth noting that SA is a free variable. It does not have to be positive. Last time we kind of stumbled a little bit on this point because we've never seen such a thing. But let me introduce a trick that will work in this problem, and later we'll formalize it so that it will work on any other problem like this. So the trick is, well, this variable is free. What will happen if we assume that it is positive? Will the problem become different? Well, the problem will become different, but its solution, its optimal strategy, is not going to become different. Why is it? Well, we see from this table that all these numbers are actually positive. So whatever Alice plays, she is guaranteed never to lose. So her security level, her optimal security level, is guaranteed to be non-negative. So in this particular game, because all the payoffs in this table are positive, or non-negative, we can assume a priori that SA is positive, not negative. Let me write this down. Since all the variables are non-negative, we can assume SA to be positive because the optimal SA is in fact non-negative. I mean, of course, formally, say if you put -1 and -1 on the right hand side, you will be able to find some x1 and x2 that satisfy this inequality, but 0, 0 will satisfy this. Sorry, 0, 1 will satisfy this. But we know that the optimal value of SA, of the thing on the right, is at least 0. And why is it? Well, because Alice will get at least 0 regardless of what she plays, regardless of the assignment probabilities. So if she plays 0, 1, even if she pursues a pure strategy, and Bob decides that, well, he will only call, which means we are here, well, here we have 0, SA still being 0 still satisfies this. So because all these numbers are positive, we can assume that SA is also positive. So we see that in this particular game there was a coincidence which allowed us to use this kind of thing. Maybe we'll discuss a little later what to do if it wasn't the case. If we were playing a game where some of the outcomes are actually negative and possibly the security level is also negative. Okay, but for now let's solve this problem. First of all, let's convert it to standard form. So I want sign smaller or equal than, not greater or equal than, and I want all the variables on one side. So I would say, let's do it this way. Minus 0 times x1 minus 1 times x2 plus SA smaller or equal than 0 minus 1 half x1 minus 0 x2 plus SA smaller or equal than 0 x1 plus x2 is equal to 1. Well, x1 x2 SA all non-negative, and I want to maximize some number z, which is in fact SA. So this is just the same problem written in standard form, and now we can apply the usual simplex algorithm. So the initial table would be 0, minus 1, 1. We'll add set variables to these two inequality constraints. 1, 0, 0. Minus 1 half, 0, 1, 0, 1, 0. This constraint is equality constraint, so to be honest, I cheated slightly. This is not the standard form. In standard form, we do not have equality constraints, but nevertheless, it is very convenient for us to have an inequality constraint because, well, we can just write it as equality. Anyway, when we go from here to the table, we convert inequalities to actual equalities by adding set variables. So here we don't have to add any set variables. It is already an equality. So we just write 1, 1, x1 plus x2, and nothing else. And the sum should be equal to 1. So let me put quotation marks in standard, because it's not quite standard, but at least standard enough for it to be very convenient for us. And finally, I want to maximize something which is just SA, so coefficient of 1 right here. And this something is there. So that's the table. Maybe okay, so let's solve this quickly. I see that I can increase z by increasing this variable, and then I see that my first iteration has to be degenerate because here I have ones and here I have zeros. So both of these tell me that you can increase only up to 0. I'll choose, let's say, the first one. It doesn't really matter which one. I'll make this 0, 0, 0. So okay, the first line. I'll subtract the second line from the first one. Sorry, first one from the second one. 0, minus 1, 0. Do nothing with the third one. So here I still have z, and I subtract this one, 0, 1, 0, minus 1, 0. So next iteration, I'll try to increase this variable, it's the only positive number over here. And once again it will be degenerate, because I see here I can increase it only up to 0. Smallest number on the right is 0. Sorry, smallest portion, 0 over 1 is 0. So we see that, I mean, when we talked about the simplex algorithm, it looked like kind of remote possibilities of ever encountering a degenerate iteration, let alone kind of 2 degenerate iterations in a row. But now you see it's quite natural. In practical problems, it just happens. So actual problems which come from some real life source, like this one, well, they do have degeneracies for some reasons. So let's see what happens here. You add the second line to the first one. Minus half, 0, 1, minus 1, 0. We leave the second line alone. 0, minus 1, 1, 0. Subtract the second line from the third one. Half 0, 0, 1, minus 1. And subtract the second line from the last one. Half 0, 0, 0, minus 1. Now we have just one choice for the pivot column. We see that the smallest portion, which is positive, is this one. So here we can increase the variable as much as we want. Here we can increase the variable as much as we want. Here we can't, we have results. And this leads us to the following table. Z minus, so here I'll have to subtract 1/3 of this row, minus 1/3. Let's see that this table is actually the last one. So 0, 0, 0, minus 1/3, and minus 2/3. So that's the optimal solution. To find out what this solution is, we find these numbers. So here I have to add 1/3 of this row, so it's 1/3. Add 1/3 of this row, so it's 1/3. And divide this by 3/2, so we get 2/3. And the corresponding variables which are basic in this case are So here we have 1, 0, 0. Here we used to have 0, 1, 0, and 1, 0, 0. So we see SA is 1/3, X2 is 1/3, X1 is 2/3. X1 is 2/3, X2 is 1/3, SA is 1/3. So I hope you see that it wasn't too complicated. In fact, well, we could have kind of guessed what inequalities over here should have been inequalities, and these were the only two inequalities. So, I mean, we could have. I mean, this problem has a total of 4 inequalities. Each pair can be pushed to their limits, but we know what inequalities out of these 4 should not be pushed to their limits. Pushing this inequality to its limit would mean pursuing a pure strategy. X1 is 0, X2 is 1. So not a good idea. Same about pushing X2 to its limit. So the only possible inequalities to push to their limits are these two, and in fact we could have solved this problem without the simplex method, but still I wanted to show that the simplex method works, that it actually has degenerate operations. And of course, the only reason we could have guessed this was our problem was really, really small. Only 2 strategies. Okay, 2 strategies to work, so the problem was very small, we could have guessed. But anyway, now we found the optimal solution. The optimal solution calls for the following strategy. You should be honest 2/3 of the time, you should bluff 1/3 of the time, and once you pursue this strategy, you are guaranteed to get, on average, at least 1/3 of the dollar. On average, of course. And this is, in fact, the optimal strategy which Alice, so for now we just know that it's the optimal strategy which she can pre-commit to. If she decides in advance to assign these 2 probabilities and announces her strategy, and Bob has to make a decision based on this announcement, well, regardless of what he is going to decide, regardless of how he is going to mix his own 2 strategies, she will always get a payoff of 1/3 of the dollar on average. And last time we also discussed that, well, this is of course very good for Alice. I mean, she knows that she has a way to pre-commit to a strategy, announce it aloud, and still be getting 1/3 of the dollar every time. Well, not every time, every time on average, except payoff. But does she have a better, can she make a better decision? Can she maybe not pre-commit to a strategy, maybe not announce the strategy and get somehow mix the strategies in some proportion and get a better outcome? And for this, we discussed that we'll have to discuss the security level for Bob. Can he guarantee, by playing some kind of mix of his own 2 strategies, that Alice will not get more than 1/3 of the dollar on every round, regardless of how she mixes her strategies. So let's discuss Bob's. Security level. Well, last time I kind of hinted that the corresponding problem for Bob should be the dual problem to the problem for Alice. So the security level for Alice, this problem should be dual to the problem of deciding what is the security level for Bob. And last time we talked about the fact that we kind of don't know what to do with such problems. First of all, here we have 3 variables, and also we have a constraint which is equality. So let me this time, instead of discussing the problem of security level for Bob, let me instead just discuss the dual problem to this one. And then we'll see that this problem is actually what we need. So let's discuss duality in this kind of context where you do have some equalities and then you do have some free variables. Well, so let me try to recall what is duality about. So let me write down once again this problem in standard form. It was minus 0x1 minus 1x2 plus xa smaller than 0. Minus half x1 x1 plus x2 is equal to 1. x1 is positive, x2 is positive, SA 3. And now recall how we approached just in the very beginning how we approached duality. Our definition was like this. Oh yes, and maximize the objective function which is SA. Our approach was, let's take some way, well, let's see whether we can make sure that this objective function is no larger than some number. And then we thought about, well, how can we guarantee this? Well, we can take these inequalities and try to combine them in such a way which will tell us the combination of these inequalities on the left-hand side is at least as large as SA. The right-hand side corresponding linear combination is such and such number, hence SA is smaller than such and such number. So we try to mix this kind of constraints with some coefficients. y1, y2. This should be kind of like C, but let me call it SB because, well, for two reasons. Once it is somewhat special, hence S, because it is equality constraint. And another reason, well, the reason for the B will become clear later. So the idea is, let's take these inequalities, or in this case equality, one of them is equality, and multiply them by y1, by y2, and by SB. And let's take the sum. This thing times y1, this thing times y2, this thing times SB. What I want to make sure is that once I take this sum, I get something which is as large as SA. So in particular, I want to make sure that the coefficient of x1 is at least 0. So let me write this down. y1 times 0 plus minus 1/2 times y2 plus SB is at least 0. So I want to make sure that the coefficient of x1 in this linear combination is at least as large as the corresponding coefficient in the objective function. If you wish, that's my objective function. I also want to make sure the same thing about x2. So I write minus 1 times y1 minus 0 times y2 plus SB is positive. I also want to make sure that the same thing holds about SA. So coefficient of SA. So y1 plus y2 plus 0 should be, let's see what happens. SA is a free variable. It can be either positive or negative. So So if I just write that this is at least equal to 1, it will be no good. Because so let me kind of traditionally say that this is at least 1, but let me explain why this is not good. If I make this just bigger than 1, then what I have is the coefficient of SA will be at least 1. Okay, that's good. But will it mean that SA is actually smaller than this linear combination? So if I have something like this, my objective function SA, and I want to compare it with something times SA. So this something is y1 plus y2. I know that this something is at least 1. Does it mean that I can write this inequality? So if this is at least 1. Can I write such a thing? Well, if SA were positive, then yes. Unfortunately, SA is not necessarily positive. It could be positive or negative. Well, so if I make this greater than 1, I can't guarantee this. Of course, if I make it smaller than 1, it also doesn't tell me anything. Once again, SA can be positive or negative. So the best thing I can do is actually write that if this is equal to 1, then this will be equal. So instead of this inequality, I'll have to put equality. That's actually the best thing I can do. Once again, the reason is I'll get a coefficient of SA, but regardless of what coefficient I get, if it is not equal to 1, I will be able to make sure that by choosing some value of SA, I will get either a number that is larger than the objective function or smaller. So I'll have to make these things actually equal to 1. Well, so these are about equalities or inequalities between these coefficients. Next, my objective function. I want to find the smallest possible linear combination of the right-hand sides. So 0 by 1, 0 by 2, plus 1 times SB. Now let's see what do I want about my variables. y1, y2, SB. So y1 and y2, I want to make sure that once I know that this objective function is smaller or equal than the linear combination of these right-hand sides, then this linear combination of the right-hand sides is actually smaller or equal than the linear combination of the right-hand sides over here. For this, I'll have to make sure that y1 and y2 are positive numbers. If I multiply inequality by a number, if it is positive, it stays the same inequality. If it's negative number, it reverses the sign. So I do want to make sure that y1 is positive, y2 is positive. On the other hand, about SB, I don't want to assume anything, because it was equality. It doesn't matter whether I multiply this equality by positive number or negative number, it's still going to stay equality. So I have SB, which is 3. So let me write down the incident again. From this problem about duality in general. We see that if we have a free variable in the primal problem, then what happens is you don't want the corresponding inequality, the dual constraint, you don't want it to be inequality, you want it to be actual equality. So if this number can be positive or negative, you can't guarantee that objective function will be smaller than the linear combination unless you make the coefficient exactly match here and in the linear combination. So more generally, if you have a free variable in the primal problem, in the dual. Another thing, if you have equality constraint in the primal, it doesn't matter whether you multiply it by a positive number or negative number. It still stays equality. So equality constraint in the primal goes to a free variable in the dual. So if you have a free variable in primal, you'll get equality constraint corresponding to coefficient of this very variable in the dual. If you have some constraint in the primal which is equality instead of inequality, in the dual we'll have a variable which corresponds to the variable by which you multiply this particular constraint, which can be free, and positive or negative. And well, quite neatly, we see that there is a duality here. Duality between free variables and equality constraints. We can kind of change the words primal and dual here and still get a correct statement. Alright, so now we do know at least how to formulate the dual problem, even if you have equality constraints, even if you have some variables which are free. We'll not reprove all the theorems about this problem. I mean, we don't have time actually. It will be quite boring if we'll be actually repeating all the arguments that we have when discussing usual duality. But still, it is true that, well, weak duality theorem holds quite obviously as the construction of the dual problem. Strong duality theorem holds a little harder, but basically because you can construct tables for this problem, tables for the dual problem, follow the simplest algorithm, it will go in kind of dual steps and converge to one optimal solution. So, well, so the prices, everything works. Well, now, what is the relation of this dual problem to this one, to the actual view? No? Let's rewrite this. In slightly different form, let's rewrite this as 0 times y1 plus 1/2 times y2 is small equal than s3. 1 times y1 plus 0 times y2 small equal than s3. y1 plus y2 is equal to 1. y1 positive, y2 positive is v3. Minus d. So we took this dual problem to this problem of deciding on Alice's security level, rewrote it slightly, and now we see that it is exactly the problem about deciding on security level for both. So we put here. If you assign probabilities of y1 and y2 to his two strategies, first inequality here is about his expected payoff if Alice decides to pursue the first strategy, or RBM, and we want, I mean, Bob wants her expected payoff to be no larger than something. Same about her expected payoff if she pursues the second strategy over here, this one. We want it to be not really large. We want to find the smallest possible upper bound on her payoffs. Well, this constraint is about, well, this constraint is about y1 and y2 being probabilities. And this, well, fits nicely with the fact that SD, the security level could be positive or negative. So that's exactly the problem of deciding what is the mixed level security level for Go. And from general duality theory, which, well, I kind of promised you that it works even in these kind of problems, we know that the optimal solution will be still the same. The optimal solution of the dual problem is the same as for the primal. So his security level, duality theory, well, doesn't really tell us right away what is his dual strategy. For this you'll have to involve complementary statements. Once you know the solution to the primal, you can find the solution to the dual by using complementary statements. But at least we know that his security level is exactly the same. So he does have some way, for now we don't know which way, to mix the two strategies in such a way that Eris is not going to get more than 1/3 of a dollar on average in every round. And now we know that Eris actually doesn't have a way to do better, regardless of whether she announces her strategy or doesn't announce it, pre-commits to it, not pre-commits to it, chooses to be rational, chooses to be not rational, it doesn't matter. If Bob is going to follow his best strategy, she will never get more than 1/3 of a dollar on every round. So if she does find a way to actually get 1/3 of a dollar on average in every round, that's her best strategy. So now we know that there is one best strategy for Bob, there is one best strategy for Eris, they lead to the same outcome. So regardless of whether they both know about their respective strategies, they still will be playing these particular best strategies. And now I hope that you are convinced that this is not a phenomenon about a particular game. It is very, very general. This game was not really symmetric. I mean, the payoff table is not symmetric. This game, well, was really rigged for Eris. I mean, she was winning all the time, and it's not a fair game. From the perspective of Bob, it's not a fair game, let's say, in this way. But still, regardless of this, we know that there is some kind of strategy which is optimal, which both players would agree is rational for them, and if at least one of the players pursues his best strategy, there is no way for the other player to get a better outcome for himself. Okay. Now, I want to make a statement which is, well, at least for me, was not intuitive, wasn't obvious. Let's take some kind of two-player game with some randomness, perhaps. Let's say the usual poker game. Then you get a hand of cards, and the other player gets a hand of cards. Then you make your bets. Then you get some other cards revealed. Then you want to make some combination out of these cards, and whoever gets the larger combination wins the bets. There are lots and lots of variations on this game, but regardless of what variation you have in mind. Right now we know that if it is two players game, and if it is zero-sum, whatever I get, somebody loses. If you don't want to cooperate, well, it's not that I know that that I will be able to actually find the best strategy, but at least I know that there is a best strategy. That in these kind of conditions, there is some assignment of probabilities to all possible strategies. A typical strategy would look like this. Suppose you get such and such hand. In this case, you should make such and such bet. Okay, and depending on whether you have to make some other decisions, for each kind of other decisions also make the actual choice that you will be making later during the game. So if you have to change your bet depending on what you see on the table, well, you have to describe if I see on the table a king, I will fold. If I see a queen, I will raise. Something like this. So there will be probably quite a lot of different pure strategies. Why is it quite a lot? Let's say that you get just 2 cards on hand. So how many choices do you have to describe? Depending on the combination of 2 cards on hand, if it is a deck of 52 cards, you have how many possible combinations? 52 times 51 over 2. So something like a little more than 1,000. So 1,000 strategies just for the choice of you see 2 cards on your hand. A typical game of poker has not only this, it has then first card is revealed, second card is revealed, third card is revealed, maybe in some other combination you get not 2 cards but 5 cards on your hand. So the number of possible pure strategies is huge. Something like 50 to the power 5 or something like this. So it's really huge. You'll get a problem with millions of constraints. You will not be able to give it the window and tell it, solve it. Well, our freeware version of window only allows 300 constraints, so you won't be able to even solve kind of one card poker game, but I mean, even the best possible linear programming packages, first of all, it's really hard to just list all the strategies. There are lots of them. Once you listed them, well, there is just no way that you will be able to actually find the optimal solution by solving the linear programming problem. It's just huge, really huge. But in principle, I mean mathematically, you know that there is one best strategy called the equilibrium strategy. It's called equilibrium because even if your opponent learns about your strategy, you write down a book about this strategy, describe every possible reply to every possible move in poker, you write the complete book, nobody will be able to beat your strategy, just because it is optimal. I wouldn't say that it's an obvious mathematical statement that is, I mean, say in a game with no chance, like chess, it is obvious before you learn about the rules, it's obvious before you kind of analyze this game that there is some optimal strategy. That by describing all possible decisions that you make regardless of what is in response to what you see on the actual chess board, if you describe all possible moves, well, you'll analyze this whole huge tree, you'll find all the responses which do not lead to a loss, well, you'll find some strategy which is the best one. That's obvious. In a game which does involve some kind of chance and lack of information. So you don't get to see the hand of the other player, you don't get, well, there is some kind of chance of getting one kind of card on the table, another kind of card on the table. I wouldn't say that it's completely obvious that there is at least one equilibrium strategy. It's not obvious that you will be able to find out about the strategy, write a book that describes it completely, and still not be beaten by any other player. But now we have proof. And that's about duality theory. Another thing is, well, yes, let's say poker is a complicated game, it has tons and tons of strategies. Our software can solve maybe, I don't know, up to 100,000 constraints, not really much more, maybe 1 million in rare cases if you want to algo it to very long. But the poker game is much more complicated than this. So how do people actually program automatic computer players which play a good game of poker? Not optimal one, not best possible one, but some kind of approximation to this solution, to this equilibrium solution. Well, actually there is kind of tons of books written about this. Let me just outline kind of some simple strategies for doing this. Well, first of all, eliminate dominating strategies. If there is a way to reason that some strategy is obviously not good, well, eliminate. It will decrease the number of strategies a little bit, but in poker it will not be kind of by factor which is enough to make the problem small. Next thing, so this is still without losing information about the actual game. Next steps usually involve some kind of loss of information about the game. So you know that, let's say, a combination of a king and a queen in the initial hand that you get is pretty good, and it is equally good if you get a king and queen, king of, let's say, red suit or black suit, spades, hearts, regardless of the suit, it's kind of equally good. So maybe let's not describe 4 different strategies depending on whether you get king of spades and queen of spades, which is one strategy, then another strategy for king of hearts, queen of hearts will be another strategy, and then we'll have 4 strategies for these 4 combinations. We know that, well, it looks like these 4 combinations are more or less the same. So there is some kind of symmetry. So let's combine them to just one strategy, which we'll call, you get a king and a queen, and then we'll use this strategy as just one strategy. Well, this will reduce the number of possible strategies by, well, quite a large factor, maybe 2, maybe 3, maybe 4, still not enough. Then people try to argue about what other kinds of combinations in the game, what kind of strategies tend to behave in the same way regardless of what the opponent plays. And then people either do it by thinking really hard about the game of poker, or they do it automatically by kind of choosing several strategies, kind of generating many random responses of the other player, and see that if some strategies cluster and get to the same outcomes regardless of the response, well, I mean cluster in the sense that you lead to similar outcomes, not exactly the same, but similar outcomes. Then maybe it's a good idea to take these strategies and combine them to just one pure strategy. Now we have lost some information about the game. We will not be able to distinguish between the individual strategies over there, but the thing is we'll get much less these kind of compressed strategies. Once we get a small enough number of these compressed strategies, let's say 1 million, we can actually run linear program solver and actually find the strategy for this compressed game. And then hope that it is actually a good approximation to the equilibrium strategy. So what I want to emphasize is, well, not the particulars of how we solve computationally hard problems like finding the equilibrium strategy for poker, but that we already know that, first of all, it is a problem that is solvable. It's not trivial. It's really a statement. There is something to the statement that poker is solvable. It's not intuitive. But it is solvable, and the reason is basically duality in linear programming. Another thing is, well, once we realize that solving poker is about solving a huge linear programming problem, well, we might as well try to develop algorithms for, well, maybe we have 10 billion constraints, we'll never develop an algorithm which will solve this using, say, our today's hardware. But maybe we'll be able to find algorithms that get an approximate solution. And maybe it's a good idea not to analyze just a game of poker, but just to analyze linear programming problems in general with 1 billion solutions and somehow find approximate algorithm which will approximate the best solution. And then not only will understand something about playing poker, we'll understand something about playing quite a lot of chance games. But it's the same underlying mathematics, which is very good. Okay, so maybe questions about these kind of things. I have a couple of more remarks to make. So, another kind of insight from just the fact that a zero-sum game reduces to a linear programming problem. Just from this one observation, we can make the following conclusion. Suppose you have a game where the number of strategies for one player, let's say non-dominated strategies, is larger than the number for the other player. So suppose maybe let me write down the previous insight that I want to say. So games like real poker are solvable, but computationally very hard. So in this sense, poker is not really that different from chess. Both are solvable if there is an obvious algorithm for solution. I mean, for chess it may be a little bit more obvious. It's just enumerate all possible strategies and see which one is best. For poker it's a little harder. We have to invent duality for realizing that there is a strategy, but still, it is solvable. But, of course, computation is very hard. That's why we try to find some heuristics, some approximations to the solution, like what we do in chess. So, instead of saying, like, in chess, it's a good idea on the third move, if the situation is like this and like this on the board, to make such and such move. Well, you don't teach chess in such a way. You just tell, in the beginning of the game, try to control the center, something like this. So that's exactly the kind of heuristic that we try to find when solving large linear programming problems, like the one for poker. We try to find some kind of clusters, like beginning of the game, and some kind of strategies which are good in this particular cluster, like control the center. Now means, if player A has n pure strategies and let's say non-dominant, and player B has n strategies non-dominated, say m is greater than n. Suppose that player A has 1 million pure strategies. So for player A, the decision is really hard. She has to choose between 1 million strategies. But player B has only, let's say, 2 possible responses. Is this game really hard? Well, the answer is no, not that hard. Because A, the optimal solution, mixes at most n strategies. Well, you just know that in linear programming problem, you push. Well, you have lots of inequalities, you want to push the number of inequalities which is equal to the number of unknowns. Well, here the number of unknowns, this will be the number of inequalities, this will be the number of unknowns. If the number of unknowns is very small, you will have to push just this number of inequalities to their limits. It means you will have only to mix this small number of strategies. So in the kind of example that I described, lots and lots of possible choices for player A, let's say 1 million, and only 2 possible strategies for player number 2. You know that the optimal strategy will be either a pure strategy or will be a mix of 2 strategies for player A. And once again, this is not an insight about some particular game. It's not an insight which kind of follows from very deep mathematics. It just follows from this one observation. A zero-sum game reduces to a linear programming problem. So we have this result. Well, of course, the actual problem would be to find the pair of strategies out of 1 million, which is the best one, and for this you still have to do the simplex algorithm. At least you know some. You will not have to mix 1 million different strategies. And yeah, and a general trick for making the security level positive. So I still owe you a description what to do. Well, if your variable is free, if the security level is free, it could be positive or negative, but you still want to apply the simplex algorithm. The idea here is to change a game to a different kind of game. So if the payoff, for the payoff matrix Aij. So I describe quite an arbitrary game, just some coefficients for the payoffs, the security level of the role player. Well, actually, we now know that it's the same for the row player and the column player, so I can just say the security level. There is only one. It's also called the value of the game. Is S, and this number could be positive or negative, depending on the actual matrix. But here's a funny trick. Then, for the payoff matrix, Aij plus T. So let's take our previous game and make the payoff to the first player larger by $2 on every possible outcome. Well, will the best strategy change? No, not the least. We just guaranteed, we can replace this game by the following game. On the beginning of the, before playing the game, we just give $2 to the first player, and now let her play the actual original game. So of course the strategy does not change. But now the security level becomes the security level is S plus T. Well, of course, the first player gets $2 in the beginning of the round and then plays the game with security level S, so the payoff is S plus T. Now choose T large enough. How large? So I want to make sure that this number is positive. Well, choose T to be just large enough to make all these numbers positive. So if T So when you translate this information to actual kind of question, how to solve a given problem, so suppose you have a problem like this one, and suppose you actually didn't think to eliminate the non-necessary strategies. So the problem looks like it has some negative traits, and it looks like maybe the security level could possibly be negative. Well, the strategy is like this. Increase all these numbers by 3 halves. Just all the numbers in the table add 3 halves. It will make all the numbers in the table positive. Solve with these positive numbers. In the very end, subtract 3 halves from the payoff. You'll get the answer to the original problem. So we'll actually never have to deal with 3 variables. Of course, in general, there are tricks to actually deal with 3 variables in quite general context, but let's not discuss this. It's really that important. But in the context of zero-sum games, so that's the trick. Okay, so first of all, thanks to all of you for coming and for listening. This is the end of the material. I will not start new material in the last lecture next time. I will probably discuss some problems. If you want, you can send me email with problems if you want to discuss. Otherwise, I will bring some problems and discuss them. And otherwise,